Welcome to section 14.2, Calculus of Vector-Valued Functions. In 14.1, we introduced the idea of a vector-valued function, which was a better way to think about a set of parametric equations, that we can group them together as one object, a vector-valued function. Now we get to actually do some calculus on them. The objectives of 14.2 are to find and graphically interpret the derivative of a vector-valued function. Then we'll try to understand and verify the properties of the derivative of a vector-valued function, and we'll do some integrals of vector-valued functions. I'll keep the objectives up at the top here. As far as what kinds of objects we're dealing with functions where you input a number and you get out a vector, either 2 numbers if it's a vector in the plane, or 3 numbers if it's a vector in space. So, first up, what are we going to try to do? Well, we're going to try to take derivatives of vector-valued functions. So here's my vector-valued function. We think of it as having a function in the first slot, a function in the second slot, and a function in the third slot, x of t, y of t, and z of t. Well, what does it mean to take the derivative of an object like this? And your clue should be, well, how did we deal with the domain of a vector-valued function? Well, we zoomed in on all the components. How did we deal with saying whether a vector-valued function was continuous? Well, we looked at all the components. So what are we going to do to take the derivative of a vector-valued function? Same deal. Just look at all the components and do the operation to all the components. So we're going to say if r of t has these 3 components, the I, j, and k. So the summary here is look at the components. If you've got a function in the I slot, a function in the j slot, and a function in the k slot, and all these functions are individually differentiable functions, then the vector-valued function has a derivative. And we say that that vector-valued function is, well, take the derivative of the function in the first component and leave that result in the first component. Take the derivative of the function in the second component and leave that one in the second component. And take the derivative of the function in the third component and leave that one sitting in the third component. Okay, so what does this actually mean? Well, it means, so like, what did r of t mean? What r of t meant in section 14.1 was for every time value, for every parameter value that you plugged in, you got a point in space. And so a vector-valued function gave you like a curve, like a helix or something, would be r of t. R of t traced out a curve in space. R prime of t is going to be the rate of change. But wait, no, r prime of t is still coming out as a vector. So what does r prime of t mean? Well, it gives you a tangent vector at the point r of t. So if r of t gave you a spiral, then r prime of t would say, well, r prime at this point is this tangent vector. R prime at this point is this tangent vector. R prime back here, we're going around this way. R prime here is going this way. So r prime of t gives you, at each value of t, it gives you a vector that tells you the direction and magnitude of like where r of t is headed. Okay, so let's see how we compute it. Wait, why does it say as follows? Oh, I skipped a page for no reason. Okay, so here's let's do an example. This is good. This one is a function that takes one number as input and gives you a vector in the plane as output. So this time we're talking about this kind of function where it takes one number as input and gives 2 numbers as output. It's a vector with 2 components. So if r of t is this vector, what's r prime of t? Good news. R prime of t is still a vector, and you take the derivative of each component. So the derivative of t plus 2 with respect to t is 1. The derivative of minus t squared with respect to t is minus 2t. That's it. That's r prime of t. What is r of minus 1? r of minus 1, there's no prime on here, so I'll plug minus 1 in for t in both sides of this equation. I'll plug in minus 1 for the t on the left, plug in minus 1 for all the t's on the right. So I get 1 minus 1. Remember, when I have a vector-valued function and I plug in a number into the vector-valued function, I'm thinking of this as like a location on a curve. Like maybe it's a spiral, or maybe it's a parabola, or maybe it's a line. But when I plug in a number into r of t, that tells me like where I am. So r of 0 will tell me the starting point for my curve. Plug in 0, I get 2, 0. Now, where did I plug in 0? I plugged in 0 into r of t because this just said r of 0. For the next one, it asks me for r prime of minus 1. Now, here's where you can get the most common misconception. You could say, well, wait, I know what r of minus 1 is. It's these numbers. And I'll take the derivative of these numbers. No, that's not what's going on here. You don't take the derivative of this. If you did, you would always get 0, 0, 0, 0, 0 for all of the r primes of everything. Instead, you find r prime of t, it's 1 minus 2t, and plug the t value into r prime of t. I was going to write some stuff in red, and then I just didn't. So r prime of minus 1, we plug minus 1 into r prime. Get 1 minus 2 times minus 1. So yeah, that's r prime of minus 1, and then let's get r prime of 0. R prime of 0, plug 0 into the derivative. I get 1, 0. What do these mean? Well, what these mean, the r values tell you a location. So like in the plane, the r values say at time 0, I'm at 2, 0. At time minus 1, I was at 1, minus 1. And then the derivatives tell you the direction that I'm headed. It tells me like the tangent vector to some curve. So r prime of minus 1 goes in the direction 1, 2. So it goes like this way. Here's 1, 2. And r prime of 0 is 1, 0, which looks like this. Notice how, because of the context, r of 0 was the vector 2, 0, and I plotted that as a point. And r of minus 1 was 1, minus 1, and I plotted that as a point. Where r prime, these are tangent vectors, this is more like where are we headed, and so because of the context of this being r prime, I plotted those as vectors in a specific location. From this information, I can kind of tell like what must be going on with r. I must be headed something like this. I was headed up, and I was headed kind of like to the northeast when I got to the point 1, minus 1, and I was headed straight east when I got to the point 2, 0. If I found more tangent vectors and put them at their corresponding locations, I would get points with tangent vectors attached to them. And I would treat these vectors differently based on the context. Okay, let's look at page 2. This says to do exactly what I just did. So graph r of t. R of t was t plus 2 minus t squared. To graph this, I can just plug in a bunch of values of t until I understand what's going on. I do want to notice that if I had just r of t was t minus t squared, this would be the regular old function y equals minus x squared. This one is similar, the one that we need to graph. This is going to be y equals minus x squared, except all the x values are too higher. So y equals minus x squared would just be a parabola with a vertex at 0, 0. This one's going to be a parabola with a vertex at 2, 0. Not my best parabola. Okay, so that's how I would do it, because I've seen a bunch of these, and I will always show you like the expert way to do it. But if you see a vector valued function and you do not know what to do with it, you can always just plug numbers in. So you don't have to think this way. As long as you know how to like fall back and plug numbers in. What numbers do I plug in? I plug in values of t. I recommend against putting x and y here. Instead, you should try to train yourself to think of the output as a single object. So at t equals 0, r of t is, well, I'll plug in t equals 0 and I get 2, 0. And I plot that as this point. And at t equals 1, I get 3 minus 1. And I get this point. I guess my expert parabola wasn't so great. It looks like I only went over by 0.5 instead of by 1. But I had the shape correct. When I plug in t equals minus 1, I get 1 minus 1. Let's try t equals minus 2 just to get the x equals 0 point. And at this point I can see that it's going to be some kind of parabola. Okay, graph r of t and interpret all 4 numeric vectors we computed above. Well, we computed this. This was r of 0. And this point, 1 minus 1, corresponds to r of minus 1. The value of the vector valued function we think of as a point on a curve. The derivative we think of as kind of like a velocity vector. Where are we headed? R prime of 0 I draw as a vector that tells me, yeah, I'm headed this way. And r prime of minus 1 I think of as a vector that tells me, well, when I get here, I'm headed in this direction. And this is r prime of minus 1. So you end up drawing them differently. Okay, so what is this? The derivative of a vector valued function gives us a velocity vector. For the curve, r of t, at any value of t. So let's say like at any time t. So what does this mean? It means like, well, you can see by plugging numbers into a vector valued function, you can see like where you are on the curve at each point in time. By plugging numbers into the derivative of a vector valued function, you can tell which direction the curve is heading. If you get a huge vector that's really, really long, has a large magnitude, that means the curve is moving really fast at that point. If you get a really small vector, like one that's barely, it's almost a 0 vector, then you know that the curve is like slowed down a lot. In this next example, it asks when does r prime of t equal 0? That would mean that the curve is just taking a break, like it goes for a while and it slows down to a complete stop for a moment. So when would r prime of t equal 0 for the following vector-valued function? Do you notice that this is a bold 0? This is the 0 vector. Remember that in Calc 3, it's very valuable to keep track of what kind of object everything is. This is, when is the velocity vector? The 0 vector. So when is the curve stopped? What would that mean graphically about, looks like there's a letter missing here too, about r of t. So this would mean that the curve stops for a moment. Okay, let's find the derivative. So we'll find the derivative and set it equal to 0, because that's what the question asked. So here's r prime of t. To take the derivative of a vector-valued function, I'd take the derivative of each component. So I'm still going to end up with a vector, and I'll end up with, well, whatever I get from the first component in the first slot, and whatever I get from the second component in the second slot. So derivative of 4 cosine t. Derivative of 4 cosine squared t, I'll have to do the chain rule. Let's see, did I do that right? So derivative of cosine squared t, the 2 comes down, and then I multiply by the derivative of the inside. Yeah, this is right. Then the derivative of the second component, I need, whoops, the derivative of 4 sine t, and then the derivative of 4 sine t cosine t. I don't really want to do the product rule. It's not that bad, I guess. So we'll do minus 4, keep the first term, and multiply by the derivative of the second. And then take the derivative of the first term, and keep the second the same. Okay, what do we end up with here? Well, my plan is to set all of these things equal to 0 to see what values of t make r prime of t equal 0. So when I'm trying to set things equal to 0, it's good to factor them as much as possible. So I'm definitely factoring out a 4, and it looks like both of the terms in the x component have a sine t in them. When I take 4 sine t out of the first term, I get minus 1. And when I take 4 sine t out of the second term, I get 2 cosine t. Over here, I don't really see any common factor except for the 4. Oh, that's gross. Cosine t plus sine squared t minus cosine squared t. Okay, so how would these equal 0? To get the 0 vector, I need, I've gone out of focus. To get the 0 vector, I need to get the first component and the second component to equal 0 at the same time. So first I'll find the values of t where the first component equals 0. That happens when either sine t is 0 or minus 1 plus 2 cosine t is 0. But then I need one of these to be true, and I need the second component to be 0. It's possible that there are no values of t where both components come out to 0. If there's no values of t where they both come out to 0, then the derivative is never 0. So we'll solve for t in all these cases, and as long as there's some t where like this the first component is 0 and the second component is 0, those are the ones that the question's asking for. So what are these? We'll just look between 0 and 2 pi. So this is 0 and pi for t. This one we need cosine t to be a half. That's at, what, pi over 3 and 5 pi over 3. So one of these are our candidates. We're looking for the places where, like, these are the 4 possibilities because these are the 4 places where the first component equals 0. But we also want this to equal 0. We can solve this. I mean, it's a quadratic. I see 2 ways to go here, basically. You could either plug all 4 of these numbers into the second component. If any of them come out to 0, that's it. Or you could solve the second equation and then, like, see which values of t work for both. I don't know. I'll solve this one, just because I'm worried that you don't remember how. So to solve a quadratic trig function, you should first get either all in terms of cosines or all in terms of sines. It looks like I've got more cosines, so I'll change sine squared t into 1 minus cosine squared t. Now I'm going to move everything over to the right side so I get some nice positive coefficients. So on the right side I'll have 2 cosine squared t minus cosine t minus 1. Then I can factor this. It's apparently going to be 2 cosine t and cosine t. One with a plus 1 and one with a minus 1. Looks like maybe this way works. Yep. So this one is cosine t equals minus a half, or cosine t equals 1. So this is at t equals 0. Cosine t is minus a half. That's like 2 pi over 3 and 4 pi over 3. Then we look at all the places where both components are 0 at the same time. It looks like the only one where the components are 0 at the same time is at t equals 0. So this says, when would r prime of t equals 0? The answer is at t equals 0. And that's the final answer. Cool. If you have access to a TI calculator, you can actually graph vector-valued functions in the plane by hitting mode and going to the parametric mode. And then you can, like, move around. I guess my answer is, like, a little bit on the wimpy side, because I only looked between 0 and 2 pi because everything involved here is periodic with period 2 pi. But technically, probably a better answer would be to say, well, because this repeats every 2 pi, the answer should be 0, and then you can add as many 2 pi's as this as you want. So something like 2 pi k for k any integer. Onto the third page. On the third page, we have the theorem that's in the book that tells you what are the properties of the derivative. Now, these properties are properties that you use properties of the derivative all the time that you learned in Calculus 1. And you tended to, like, prove them all one time and then forget the proof. And mostly you think of these as just, yeah, this is how the derivative works these days. You usually don't think of these as like surprising math facts anymore. But a theorem is a surprising math fact. So, like, there was no guarantee in advance that this was all going to work out for us. It just did. So I'll just write down what this theorem is. Like, what are all the pieces that we care about? And then I'll just prove like one of them, not all of them. What order do we want to do these in? Okay. Mostly these rules will look like, the reason I bring up the Calc 1 derivative rules is that mostly these rules will look like, oh yeah, this is how derivatives work. And the point is to connect this to what you already know about derivatives of functions that are not vector valued. Okay, so the first one is that if you take the derivative of a constant function, you get 0. Okay, this like, yes, of course the derivative of a constant is 0, but like these arrows actually make the fact a little bit different of a fact. Like an example of this is if your vector valued function was the vector valued function 3, 6. The way this vector valued function works is you plug in a value of t, and the function tells you 3, 6. It's a constant function. You might complain, you might be like, what? No, it's like 2 constant functions at least. But remember, we're trying to think of this whole object as a function that takes a number and gives you back a vector. So this is what a constant function looks like now. What would happen if you took the derivative? When you took the derivative, you would take the derivative of each slot. The derivative of 3 is 0, and the derivative of 6 is 0. And this vector, 0, 0, would be your derivative. Well, that's what this says, the 0 vector. So this says if your whole vector is made of constants, then its derivative is a vector made of zeros. Okay, next up is that the derivative respects addition. So if your vector valued function is the sum of 2 vector valued functions, then you can just take the derivative of each one. And add the results. The third one is a little bit strange. The third one combines a vector valued function with something that's not a vector valued function. It's like a regular old real function. It says, what if your vector valued function is multiplied by a function that doesn't give you vectors? I don't know. I guess I'll call it f of t. I've got an arrow on the u to show you that it's a vector valued function, and f of t might just be like t squared, or cosine t. It's not vectors at all. This tells you that there's a product rule even when one of the functions is a vector valued function. You can do the derivative of the first times the second plus the first times the derivative of the second. The fourth one is a chain rule. It's a chain rule where there's a regular old function, a real valued function, inside a vector valued function. U of f of t, take the derivative of the whole thing, that you get the derivative of the vector valued function times the derivative of the real valued function. So it looks like the regular old chain rule, and The difference is that one of the functions is vector valued. Yep. The fifth and sixth ones are more product rules. These product rules are the same product rule again, but one of them you have to be very careful. The reason is that if you have two vector-valued functions multiplied by each other, well, how can you multiply two vectors by each other? There's two ways. You could multiply two vector-valued functions together using the dot product. Or you could multiply two vector-valued functions together using the cross product. One of these we have to be a lot more careful than the other, because cross products, the order matters. So hopefully the way that you memorized the product rule makes it so that your product rule works, even with 0.6 here. Basically you keep everything in the same order. So you can do like the derivative of the first times the second plus the first times the derivative of the second. And that rule works just the same with the cross product. As long as you've got like u, v, if it was u cross v, then all of your results are all u first and then v. If you learned your product rule as, what's the wrong way to learn it? I mean, it's not wrong, but if you learned your product rule that fg prime was f prime g plus g prime f, this is a true product rule for real valued functions, but this is an unfortunate order to learn the product rule in, because this rule doesn't work anymore if you're talking about cross products. If you learned your product rule as f prime g plus f g prime, this way is good, because it continues to work with regular old functions, and it also works with dot products of functions, of vector-valued functions, and it also works with cross products of vector-valued functions. So it's sometimes just valuable to memorize things in the right way. So I don't want to prove all these. The proofs are like not all that interesting, but I don't want you to feel like these are just like rules that we made up, and then like your job is to believe the rules. I don't know. It seems really miserable. So we should prove at least one of them. So I'll just prove number 4. So the claim is that no matter what functions I have, if I take the derivative of u of f of t, that I'll just get u prime of f of t times f prime of t. How do these proofs look? Well, because the derivative of a vector-valued function is defined by just breaking everything up into components, what we'll end up doing is we'll end up breaking everything into components and then putting it back together. So we'll say, suppose u of xy is, like, what does a vector-valued function do? Well, it has something that it does to x and something that it does to y. Oh my gosh. That's not right. The kind of object we're working with takes one number as an input and then gives two numbers as an output. So this is not true. This is not how this works. Our vector-valued function, it does have two numbers as an output, but it only has one number as an input. So let's say that our vector valued function looked like this. Then what is u of f of t? Well, u of f of t is we plug f of t in for all the t's. And then we're trying to show something about the derivative of u of f of t. So we'll just take the derivative of both sides. Okay, well, the derivative of a vector valued function is you take the derivative of each component. Inside each component, I use the old chain rule from Calc 1. So I'll have a prime of f of t times f prime of t in the first component. And in the second component, I'll have b prime of f of t times f prime of t. What are we doing on parentheses? Looks okay. Then from the properties of vectors, this f prime of t is a number. It's just a scalar, so I can factor it out. So I'll end up with a prime of f of t, b prime of f of t, all times f prime of t. And what is this that's left over? Well, what this is this is the derivative of u, but with an f of t inside of it. And that's what we wanted to show. This left side is the left side of the claim, and it equals this right side, which is the right side of the claim. There's nothing like glorious about this proof. That's why we're not going to do all 6 of them. But what is it that makes these 6 statements true is essentially that the definition of the derivative of a vector valued function is you take the derivative of the component functions. And because it's just based on the derivatives of these component functions, all the rules from before still work. I don't know, these proofs are kind of cool because it's like very surprising that the product rule would still work with cross products and dot products, but we're not doing them. It takes too long. Onward. Okay, we're going to do some integrals. This shouldn't be too much of a surprise. The plan was to just do some calculus on vector valued functions. We're mostly doing derivatives, and mostly we'll do integrals later at the end. But what is the antiderivative of a vector valued function? Well, you get one guess, and you're right. If you want to do anything to a vector, your first guess should be to do it to each component. So what do I mean by the integral of r of t? Well, I mean a vector where I integrate the first component, I integrate the second component, and I integrate the third component. Now, there's a little bit of an issue, which is that when I do an indefinite integral, I get a plus c. Since I'm doing 3 different indefinite integrals, I'm technically going to get a c1, a c2, and a c3. So I'll show you how we deal with that at the end. Is it printed in here? No. Okay. So let's do it. The antiderivative, I guess I'm just going to say the indefinite integral of this vector valued function is still a vector, and I'll do the integral of each component times dt. So the integral of minus 5 dt is minus 5t plus c. I'm going to call it c1, because I know there's more c's on the way. The integral of 2t dt is t squared plus c2. And the integral of 7t cubed dt is 7/4 t to the 4th. plus c3. Now what do? I don't want all these c's. What I can do is I can notice that this vector is made up of two vectors added together. It's actually minus 5t, t squared, 7/4 t to the fourth, plus c1, c2, c3, and c1, c2, c3 is a constant vector. So this will be my final answer. If you write just plus c with no indication that it's a vector, that's wrong. The data types of the objects in this class are so important, or you get completely buried as we get deeper into the class. So the integral of this vector-valued function is this new vector-valued function, but well, there's actually lots of options, and so we have plus c, and there's really like 3 c's in here, so it's the vector c. Next up is, sure, let's do some of this integral. We just do the integral of each component. So what's the integral of sine 3t? The integral of sine 3t is 1/3 cosine 3t. Or am I off by a minus? I'm off by a minus. The integral of 5e to the 6t, that's 5/6 e to the 6t. And notice that I need plus c on all of these, but I'm going to remember at the end to put plus c, the vector c, and that will handle my c1, my c2, and my c3. This one, I'm not doing that in my head. So we'll go off to the side and try to just write down equations, things that are true. So off to the side, I'll say, here's what I'm working on now. And then let's get this to work. So I want to do a trig substitution. To do a trig substitution, I don't want a 3 here, so I'll factor out the 3. Because the key to all trig substitutions is that all the nice trig identities have a 1 in them. Phone going off in class. I don't know if that even transmitted, but my phone rang just then. Okay, for t squared then, I'm hoping that this is 1 plus something squared, and the something is going to be tangent theta. Well, 4t squared is 2t, the quantity squared. Then I'll let 2t equal tangent theta. I can take the derivative of my substitution. And then finish my substitution. So 2t is going to be tangent theta. I don't have a 2 dt, so I'll solve for dt. Get all this substituted in. So I still have 1/3. 2t is tangent theta. dt is half secant squared theta d theta. And then the point of all this was that 1 plus tangent squared theta is a nice trig identity. In fact, 1 plus tangent squared theta is secant squared theta, so these cancel. So I end up with a 6th integral of d theta. Integral of d theta is I add up all the little bits of theta, that's theta, and over here I can solve for theta. Theta is arctangent of 2t. Because I wrote all this as an equation, and I even did it in a different color, it's easy for me to jump back into where I was. So the integral of the third component was a little bit harder, but I've got its answer here. It's a 6th arctan 2t. And then all the plus c's I can group together. as plus c1, c2, c3. Like so. Okay. What other Calc 1 could we have done? Like, the point was we introduced vector-valued functions in 14.1. Then we did the derivatives of them. Now we're doing the integrals of them. This is an indefinite integral. Next up, we could try to do the definite integral. I'm pretty sure this is supposed to say vector-valued function. I don't know what else I don't think it could be an R. I think it's vector-valued function. Where f, g, and h are integrable is, well, just go in and do all of the pieces individually. So if you want to do the integral from a to b of your vector-valued function, dt, what this means is to do it on each component. And that's the main thing you should take away here, is if you want to do calculus to a vector-valued function, you basically do it by doing calculus to each component individually. I don't think we even have an example for this, because we normally won't just integrate a vector-valued function. We'll have some reason to do that. And those reasons are in 14.4 and 14.5. So let's just summarize what happened here. I think I kind of want to go back to like the first page. This is the summary. Like, look at the components if you're doing calculus to a vector-valued function. The objectives were we wanted to find and graphically interpret the derivative of a vector-valued function. That mostly happened, well, finding the derivative we did on page 1. But then we really got into what is like the physical meaning on page 2, where the derivative of a vector-valued function was another vector-valued function, and it gives you the velocity vectors, where you think of the original function as giving you the positions at various times. The derivative gives you the velocities at different times. And if you draw those velocity vectors on starting on the curve at the correct spots, then you can watch, you can kind of see velocity vectors pointing the right way. In step 2, objective 2 was to understand and verify derivative properties. These are mostly, well, the same derivative properties that worked in Calc 1 work in Calc 3, just you have to do them one component at a time. This was them. We've got the constant rule, the sum rule. We got a constant multiple rule. But it's kind of like a product rule, really. You kind of got 3 product rules here. And then the fourth one was a chain rule where there's a real valued function inside a vector valued function. Keep track of the data types of the objects you're working on, and use the rules whenever you're stuck. And then the main rule you need to use is that to do calculus on a vector-valued function, you look at its components. This carried us through the third objective too, where we just integrated vector-valued functions component by component. That should do it for 14.2.